Okay. Oh. Okay. So welcome everybody to the CUNY representation theory seminar. Our first speaker of the semester is Miodrag Ivanov, who will tell us about quantum groups of finite representation type.
All right. Thank you very much. Thank you for accommodating my talk, and thanks all for showing up in this online setting. Nice to meet you all. So I'm going to talk about, today I'm going to talk about quantum groups of finite representation type. Just before I start, I just want to mention that I had a bit of a scare with my internet this morning, so hopefully everything goes smooth. If it doesn't, my apologies in advance. Hopefully we'll come back and just we'll be back here all together.
Sorry, I just want to interrupt for a second. My internet could also be shaky, so if it closes, stand by and it'll be up and again in a minute.
Now I'm posted in the meeting as Miyuki Tsushima. My photo and Miyuki Tsushima.
That's not my fault.
Sorry, everybody. We're having just a muting problem. Mio, could you unmute yourself on your computer? Okay.
Yeah, I was. Yeah, I'm supposed to be unmuted on the phone,
okay.
and yeah, and I'm using the iPad. Yeah, sorry
okay.
about that.
Okay, great.
So K will be an algebraically closed field. So let me recall the definition of an algebra of a finite representation type. So an algebra, and we will be talking about at first about a finite dimensional algebra. Everything is over an algebraically closed field. If there are only finitely many isomorphism type of indecomposable finite dimensional representations or modules. So of course, some examples, just if you get K, obviously, or K of X mod X squared, just polynomials mod X squared, or even K of X mod any polynomial F of X. That's an algebra that has only finitely many indecomposable. We know that from just a structure of modules over PIDs, and if it's annihilated by F of X, then they're going to be only finitely many indecomposable modules. Here are some other examples. For example, this matrix algebra here, not really matrix algebra, but just the upper triangular 2x2 matrices. The stars are supposed to be just arbitrary elements coming from the field K. So if you take this this algebra of dimension 3, this has only finitely many indecomposable modules, and actually it has exactly 3 indecomposable modules. It has 2 simple modules. And 1 module that's of dimension 2, and it's an extension of one of the simples by the other. So it's a uniserial module of length 2. So I'm just going to kind of draw a picture of it like this. Then another example, the 3x3 upper triangular matrices. That actually has exactly 1, 2, 3, 4, 5, 6, I believe, if I count correctly, 6 indecomposable modules. And you can actually play some games here. If you can actually erase one of the stars in that upper triangular matrix, and that still gives you an algebra. If you erase, like, for example, if I erase I think this star over here, that still gives me a subalgebra of this, and that's still a finite representation type. So that's a few examples. Of course, you can generalize this to be n by n upper triangular matrices, and for those who may know a little bit, this is just the so-called algebra of finite type of Dynkin type A, and this really AN. So the first one is A2, and the second one is a type A3. But just some examples. So now, how did these come up to be? Here's a classical result. If you take a finite group, so I'm gonna look at this this thing over here. So notability, I actually have a little hand that I can use to show. Unfortunately, I don't know how to do this on OneNote. So if you have a finite group of characteristic P, then G is a finite representation type. And by G, I mean the group algebra. So the group algebra has only finitely many indecomposable modules. Exactly, so if and only if, so it's an if and only if here, it's supposed to be an IFF. Its Sylow P subgroup is cyclic, or are cyclic if there's more. They're all isomorphic, of course. So that's a classical result, and this result actually shows where this whole definition came from. It actually came from just modular representation theory. And let me just say, if anybody has any question at any moment, please feel free to interrupt, ask question. Just unmute and just ask directly. I may not see you if you raise a hand or do or just asking in chat. So this came from modular representation, from work in modular representation theory of Brouwer and Thrall. And this there's a very nice expository paper of Ringel where he goes over these works and results. So their work, Brouwer and Thrall's work, led to the so-called Brouwer-Thrall conjectures. So Ringel says there that apparently Brouwer and Thrall initially noticed that if they look at finite group algebras, there's some very interesting things happening. Either they were having just finitely many indecomposables, or if they didn't, they had infinitely many indecomposables in all dimensions. So, but they initially, apparently, says Ringel, they were thinking this is probably a problem for graduate students. But I think they were actually, so it appears that they were thinking about the problem, and they were thinking about it quite a bit, but weren't weren't able to do any progress. So the question is, if a finite group is not a finite representation type, so has not just finitely many, but infinitely many representations, that is follow that it has infinitely many representations in all dimensions or in many dimensions. So what do I mean by this? Let's just introduce a new definition here. So here I'm going to introduce this notation here. The rep AD, so D is going to be just a positive integer, and rep AD will denote the set of isomorphous types of indecomposable A modules of dimension D. So this is just a set, and I'm just looking at isomorphous types. So let's say I'm picking up one indecomposable module of each isomorphous type, and they will be of dimension D. In the previous example, we had two simples that were one-dimensional, and there's in this 2x2 upper triangular matrices, two simple one-dimensional modules. So there I would have rep A1 would have two elements, and rep A2 would have one element, and then they will everything else will be empty. There's no representations, indecomposable representations of higher dimension. Going back to this definition, so here are the two Brouwer-Thrall conjectures. So the Brouwer-Thrall one, naturally it led to the introduction of this notion for finite dimensional algebras, not just group algebras. So the first one says that if if you have indecomposable modules only up to some dimension, so if the representation, if there's no indecomposable modules larger than some dimension, so if for large enough D, the space of the representations is empty, then A should have finite representation type. The second Brouwer-Thrall conjecture, which is a little bit stronger, says this. Well, in fact, if the representation space is finite for large enough D, then A is a finite representation type. Or put in other words, as you might see it sometimes, if A is not a finite representation type, then you have infinitely many dimensions, and in each of these dimensions, you will have infinitely many indecomposables of that particular dimension. So that's the question that we're in, Brouwer and Thrall were initially observing and asking that it should, conjecturing it should be correct for group algebras. But then naturally it led to this being posted as a question for any finite dimensional algebra. Of course, you can ask it. So now these questions are known to be, these conjectures are now known to be correct. So they're known as theorems, and their results over algebraically closed fields. They're due to Nazarova and Reuter back in the 60s and 70s. It's a very hard work. They proved it first for incidence algebras, and so there was this, then there was several steps. I'm not going to go into details, but so that's a theorem now, and landmark results in the field of finite dimensional algebras. By the way, I should say that the first one is known to not only hold over algebraically closed field, but over infinite fields, and also over the so-called Artin algebras. An Artin algebra is just an algebra over a commutative Artinian ring. So that's a slight generalization of finite dimensional algebra. And so an Artinian algebra over a commutative Artinian ring. So just a slight generalization. And that first conjecture works in this higher generality, and there's other approach to that due to Auslander. So a landmark work which led also to introduction of Auslander-Wright sequences, and so on and so forth. But one of the things that I want to take out of from this discussion is that now, if you take if you take a finite dimensional algebra, you can equivalently define finite representation type by saying that in each dimension you have only finitely many representations, because by the Brouwer-Thrall conjecture, that's if you have only finitely many dimension in each finitely many representations in the composable representation in each dimension, then by this statement, A has to be of finite representation type. So in order to go to what I want to do, so what I want to do is actually look at infinite dimensional algebras. Is there some notion of finiteness in representation type for infinite dimensional algebras? And I'm going to motivate by showing at least maybe one or two examples. So going towards that, I have to introduce a slightly more general notion of dimension, namely that of dimension vector. So here's dimension vector. So what is a dimension vector? So take a finite dimensional, so when I say rep A, I mean finite dimensional modules, as we see here. And when I say a dimension vector, you take this finite dimensional module and you look at each of the simples and record its multiplicity. And then you create a vector. So suppose it has 3 simples, you call them S1, S2, S3. And if in that composition series, we know all composition series are equivalent, of course. And in that composition series, you have S1 3 times, S2 7 times, S3 1 time. You just call that vector 3, 7, 1. Okay, so that's the dimension vector. The dimension vector records the multiplicity of simples of each simple in a composition series. So technically, the dimension vector will be a vector in this space. You take the integers, and a direct sum of copies of the integers as many times as you have simple A modules. So the EIRR of A stands for simple A modules. As usual. And simple finite dimensional. Everything I'm talking about is about finite dimensional modules. So if you have an infinite algebra, of course, you may possibly have infinitely many simple modules, not just finitely many as you have for finite dimensional algebra. So then I will be able to introduce this definition here. So take A to be just any K algebra. So it could now be infinite. Again, K is algebraically closed. And we're going to say that A has finite representation type, and you see the star here because this is actually also called discrete, but I want to call it finite representation type just because it's a bit more suggestive. If it satisfies this property, given any dimension vector, so a dimension vector is something with non-negative, non-negative entries in Z, and only finitely many will be non-zero. So something in Z to the power of the irreducible modules. So if we say that it's finite representation type, if given any dimension vector D, the how many, we have only finitely many representations of A, indecomposable representations of A in that dimension vector. So the rep AD, just by an extension of notation, means the isomorphism types of indecomposable representations M, which have dimension vector D. Okay, so I'm going to look at how many indecomposables are of that dimension vector, and I'm going to say that ask that there are only finitely many. Now, if A was to be a finite dimensional algebra, this immediately reduces to A being a finite representation type as per that definition, because there are only finitely many dimension vectors. You know, the dimension, how do you do the dimension? You just add up the entries in this dimension vector and just see how many simples you have in total. Each simple is, is one-dimensional. I should say that if you have a finite dimensional algebra, this is Morita equivalent, so it's for its representation theory. This is Morita equivalent to an algebra that has all its simple modules one-dimensional. This is very simple, just a very classical Morita equivalence fact. And then, you know, the dimension is counted by just adding up the number of simples that you have. So just counting the weight, so weight of this dimension vector. So you have only finitely many dimension vectors in any weight. And then if each of those produce only finitely many indecomposable representations, it means that in total, in each dimension, you have only finitely many representations, if A is finite dimensional. But if A is infinite dimensional, there's a problem because you may have infinitely many simple modules of dimension 1. And here's this example here, just K of X, just polynomials over the field. Now we have, remember, K is algebraically closed, it's not finite. So we have infinitely many symbols. Each symbol, of course, corresponds to maximal ideal. So maximal ideal is just the form X minus lambda, where lambda comes from K. So we have infinitely many symbols. We can just say there are finitely many modules of dimension 1, because there are infinitely many. So that's why we have to bring in this kind of definition. And this is why it's also called discrete, because you can't really say it's finite. It doesn't have finitely many representations, but if you kind of just take a little piece of it, it's locally, it looks like a finite representation type. And locally here it does actually, can actually be formulated in a word which really means localization, and it has to do with localization of categories. So there's a definition, an equivalent definition of this, where you could say you take a K algebra and you take the category of finite dimensional modules, and you ask that all its localizations in the sense of localization of Brooklyn categories are a finite representation type. and this is equivalent to saying this. So I'm just saying that there are equivalent ways of saying this, but this is also one of the reasons this is called discrete, and this is how it's called usually in the literature.
Mio,
And this
I'm sorry, Mio, can I interrupt you for 1 second? Because it's a little staticky.
so can you see the, okay, so you still see the other, okay. All right. So, so K of X is one of these algebras of discrete representation type, or infinite dimensional but finite representation type. Given any, if you fix a dimension vector, there are only finitely many indecomposable modules of that dimension vector, and we all know by just the usual, the theory of modules over PIDs that if the only dimension vectors where you have indecomposables are dimensions of the type 1, 1, 1, 1, 1, 1. So all ones. So that's one example, and there are other examples that we'll see later on. So now I want to move to, and again, if anybody has any question, please just let me know. So I want to move to quantum groups because this is, we're gonna want to investigate quantum groups of finite representation type. So I just wanted to say this comparison groups versus algebras. So I have here so two columns which are supposed to make a comparison between a bare algebra and a group algebra, or later on a quantum group. So the main difference is that a group, so when you consider the group algebra and you consider just the bare algebra, the main difference is that the group algebra has a tensor product of representations. If you take two G modules, you can take the tensor product of those two modules and you can form a new module. So that's exactly what's happening in a quantum group. In a quantum group, or just the Hopf algebra, there's no really good definition for a quantum group that other than being a Hopf algebra. So I'm going to try to sort of define what a Hopf algebra is. And what you should think about is that the motivation is really just having this additional structure of taking tensor products and taking duals of representations. So what's a Hopf algebra? First of all, it's just an algebra, a usual algebra, but it has some additional structure that allows one to introduce exactly such a tensor product. So take two modules, two representations, and let's say finite dimensional still, and we want to introduce a structure on V tensor W. We want to make that an H module. So for that, what we need is a map delta from H to H tensor H, this delta. Once you have that map, well, take an A and H and apply delta to it to write it as a sum of BI tensor CI. So we have this delta of A. And then you simply define A times V tensor W, as you see in this box over here, to be equal to the sum. And you take the first BI and you act on it on the first component of the tensor product, and the second BI acts with that on the second component. This is actually well defined. Of course, the delta of A may have various expressions as a sum of monomials, but this turns out to be well defined. No problem here. The Hopf algebra has also two other maps, sort of an augmentation map epsilon here, and one map that's S from H to H that's called antipode. But the main thing is that you have this tensor product of representations. So to just give you an example here, if you take a group algebra, how do you define a tensor product of representations? You take a G, take this G, and once you want to act with G on V tensor W, you just apply G on the first and G on the second. Well, this can be encoded exactly as it was before with this delta. So what's the delta map? The delta map is just the diagonal map, which takes delta of G to equal just G tensor G. And by the way, there's also an antipode, and it's perhaps interesting to note that S of G is just G inverse. So the antipode is just to say that the antipode is kind of like an inverse. Like you have in groups, you have inverses. In a quantum group, you have some sort of a a map that's analog to taking inverses, but slightly more complicated. So another example, if you take a Lie algebra, and you take the universal enveloping algebra of that Lie algebra, it's also well known that the representations, let's say finite dimensional representations of of U of L, are this equivalent to the finite dimensional representations in the sense of Lie algebras of L, of the algebra L. But you also have a tensor product of representations, and if anybody is working or just uses this, will immediately notice that if you actually think about the formula of how some element in L acts on V tensor W, it acts very nicely. Just goes that H acts on the first, and then H acts on the second component, and you add these up. Well, this can be also expressed by saying that our delta is going to be, so let me just write this delta here. So delta, let me just do this, delta of H is just H tensor 1 plus 1 tensor H. So that's the delta that produces this action on the tensor product. And similarly, if you have just for other examples, if you have an algebraic group, then the rational representations of that group also have a tensor product structure, and it's very similar to what I've shown before for groups. Similarly, if you have a compact group, the continuous representation, so for each of these structures, you have some sort of appropriate representations. For a group, for an algebraic group, you want to look at rational representations. This is what this R is supposed to mean. For a compact group, which has a topology, you want to look at continuous representations. So this is what the C is supposed to mean. And it also has a tensor product and also has duals. I'm not showing much about the duals, but the point is that in all these examples, you have this additional structure on the category of representations. And I need to say a little bit about this category of representations, because whenever, especially when you have an infinite dimensional situation like this one over here, like this one over here and like this one over here, you have possibly and usually infinitely many irreducible representations. So it's no longer a finite situation. It's going to be an infinite situation. So you cannot say finite representation type. You must say discrete representation type, or you just mean finite representation in the world of infinite dimensional algebras. And the category, now we're going to look a little bit at this category of representations. So let's say rational representations of an algebraic group. So this category over here. And here's what happens. If you take an arbitrary algebra and you look at finite dimensional A modules, so just representations of the algebra A. Okay, so let's just look at this category here. So this category of finite dimensional representations, or you can even look at the so-called locally finite A modules. These are modules that are just sum of their finite dimensional submodules. This is a category which is sometimes called a linear finitary category. It's actually, this is introduced by Takeuchi, and he calls it a category of finite type, but I don't want to call it this way because it would be very confusing, since I already talked about finite type. So linear finitary category. So this is a category which behaves exactly like representations of an algebra, like finite dimensional representation. So what do I mean by that? That category is linear, so it's abelian, it has finite direct sums, and its objects are finite length, and each simple module is finite dimensional. So you're in a linear category, you can define dimension of an object just as over the endomorphism ring. So something that behaves a lot like finite dimensional A modules. Something like that, in general, may not be representations of a finite dimensional algebra, but we see that for a finite dimensional algebra, something like this is, representations of A is of this type. And it turns out that this algebra, this category, is equivalent to the so-called category of co-modules over a certain co-algebra called A0, which is called either the finite dual co-algebra or the space of representative functions. So here is the space of representative functions. So this takes a co-algebra structure. What's a co-algebra? The co-algebra is really just the dual definition of an algebra. If in an algebra you can multiply elements, in a co-algebra you take an element and you can split it into sort of constituents. But in order to make this definition correct, you need to go to the tensor products of the co-algebra with itself. So exactly like we had before, a co-multiplication. So this notion of co-multiplication appears yet again here. And let me just briefly define what the space of representative functions is. It's exactly what you hear. You take functions, you take representations of the finite dimensional algebra. So you just take this, any kind of representation, and now I'm going to fix a basis of the representation vector space, so that I have rho defined on A with values in n by n matrices. And what's going to be rho of A? Rho of A is going to be a matrix. And by definition, I'm taking all these functions that appear as coefficients in these matrices, and I'm spanning a big space out of them. And I should not say rho ij, I should just say span of these. So it's the span of all these rho ij's.
Sorry, is your statement that any linear finitary category is equivalent to a category of comodules over some coalgebra?
And that's right. That's what I was. Yes, that's right. That's very. That's exactly what I'd like to say. That any such category is a category of comodules over coalgebra, or finite dimensional comodules over some coalgebra. And there are categories of this type which do not come from, do not present themselves as representations of an algebra, of finite dimensional modules of an algebra. So really you need this higher generality of, slightly higher generality of co-algebras. But that's really not that much of an issue, because a lot of times you can think of a modules as co-modules as modules over the dual of the co-algebra. So if you, so just briefly here, once you introduce this co-algebra here, A0, how does this work? If you take a representation V and you fix a basis in this space, well then each, as I said in this description, you take the action of an A, and that produces some coefficients, rho ij, which are the coefficients of your representation. And how does this A0 become a co-algebra? Well, simply you define this co-multiplication D, delta, this, think of it as a kind of a diagonal map. Just say delta of rho ij is equal to rho ik tensor rho kj. So that's going to be the map of the co-algebra. And how does this V become a co-module? Well, what is a co-module after all? Well, a co-module needs to have, if a module has an action, a co-module as something that goes in the other way, right? So it's going to be a map from V to V tensor, this space that I defined, and you simply encode these coefficient functions here. And everything here is well defined. And I should also mention that there's another definition of this space. You can simply take functions f such that these f separates variables in a sense. If you apply f of a b, this becomes simply a sum of gi of a times hi of b. So there exists such functions, gi, hi, such that when you apply f of a b, you get this. And in particular, if you think about, let's think about a morphism from a to k. So that's a one-dimensional representation. A one-dimensional, so a morphism would simply have f of a b equal f of a, f of b. So in that case, you simply have f to be such a representative function, so that thing goes in there. So that's of course those are one-dimensional representations. So this is just comparing what we have here for an algebra and for coalgebra. You see that here you have a coalgebra map going from V to V tensor the coalgebra. For a module, you have exactly the opposite thing, a map going from A tensor M to M. All right, so why do we need these? As exactly as Josh was saying, every category, every finitary category is actually equivalent to a category of comodules. And let's just go again to the example of algebraic groups. So if you have an algebraic group and you take again the rational representations of that algebraic group here, the rational representations turns out to be exactly the category of comodules over the algebra of functions on that group. So the algebra of functions has an algebra structure, but also it has a co-algebra structure. And it's just think about it. What are you doing? You're taking the group. When you take functions on the group, you're kind of taking a dual type of objects, right? Whenever you have some object and you take functions on the object, you're somehow doing it's a duality there. So if the group had a multiplication, then the algebra of functions would naturally inherit a co-multiplication. It just happens that functions on varieties also have algebra structures. So this O of G has both an algebra and a co-algebra, so it's in fact a Hopf algebra. So for this example, I just wanted to do one example and show you how this looks like in this particular case. If you take GLN, just the n by n invertible matrices, then the O of G looks exactly like this, like in this example here, and this is the delta and the epsilon. So the delta of Xij looks exactly like it looked in the previous example, and that's natural because this is how matrices act on a vector space. So this comes exactly from that, and delta of T is T tensor T, where T is the inverse of the determinant of the matrix, and epsilon of T is 0. So this is showing how the co-unit is defined, and there's also an antipode. I didn't want to show it here so that I don't overload this, but it's like in an algebra, in a Hopf algebra, once you have these maps, the antipode either exists or it doesn't. It's like when you take a semigroup or a monoid. Either that monoid is a group, that means all elements have inverses, or it doesn't. So and the same thing happens in a Hopf algebra. In once you have multiplication and co-multiplication, which are naturally compatible. And in this situation, the antipode exists, and if it exists, it's unique. So in this situation, we see this H is commutative, is a commutative algebra. And the same thing happens if you have a compact group. The compact H, the compact representations becomes H comodules for an appropriate Hopf algebra. And here's another example that is probably familiar to people. If you take the group, the circle group T here, and you take the compact representations of this group, these are exactly H comodules, where H is this Hopf algebra here. It's actually the group algebra of the integers, and this is nothing but Pontryagin duality. So this is just a particular instance of Pontryagin duality, as I mentioned here. So the general philosophy is, we've seen that if you take an infinite dimensional algebraic group or compact group or something like that, what you get is not really necessarily the category of finite dimensional A modules, but really the co-modules. So the general philosophy is to think of H comodules, where H is a Hopf algebra, as representations of some of the category of representations, or maybe regular representations of some quantum group Q. And the thing is here that in general, what we had before, the examples that we had before were of regular groups, and that produced commutative Hopf algebras. But in general, if we want to look at non-commutative and non-cocommutative situations, and in that situation, there may not be some underlying group that produce this category. So we just think of that as the category of representations of some abstract quantum group lying in the background, which we don't necessarily have. But in order to really work with that, we can just work with this category of H co-modules. Historically, first when people were looking at Hopf algebras actually appear from topology, from work of Heinz Hopf, but those were also algebras that were either commutative or co-commutative. Co-commutative means that this co-multiplication has the analog of commutativity. The first example of non-commutative and non-cocommutative Hopf algebra was really this Sweedler algebra that I'm showing on this example here. So this is has two generators and relations, and these are relations g squared equal 1, x squared is 0, and xg and gx anti-commute like this. And here are the definitions for the delta. So an element that has this feature is called a group-like element, and an element that has this feature is called a primitive. And you really can think of these as analog of morphisms and derivations. So this is the analog of a morphism, and this is the analog of a derivation. And they're like very precise ways that these appear in Lie algebras and in various other places where derivations and morphisms are exactly these kind of elements. So this was the first example, and it quickly followed, other examples quickly followed the Taft algebras, which are a generalization of that. The Taft algebras are just, replace the 2 by n, so you have these formulas over here. So don't really worry about, if you haven't seen this before, don't worry about remembering these formulas, but they're not very difficult. G to the n is 1 and x to the n is 0. And x and g and gx anti-commute, but you need this, there's no sign here, although you could put a sign. This omega here, which is a primitive root of unity. And delta and epsilon are defined exactly the same way. But what's to take perhaps from this example, that as algebras, they are really the path algebra of this quiver. So this quiver here is the quiver of type so-called an tilde. Just this, what this picture here represents is just a graph, an oriented graph with n vertices and arrows going the same way. Whenever you have such a picture, you can define an algebra by saying the elements of your algebra, the algebra will be spanned by the paths that you see here. And when you take two paths, if they can be concatenated, you declare the product to be the concatenation. If you can't, you just simply quit and say the multiplication is 0. And once you get such an algebra, you can mod out by relations. And in this example that I gave here for Taft algebras, you mod out by relations, which are all the paths of length n. So that's that's a very classical type of algebra, very important. If you don't mod out by any relation, by the way, you get an algebra that's actually a finite representation type in the sense that I mentioned before, which I should really call discrete representation type. So this is another example, an infinite dimensional algebra that has this, this property. Nevertheless, we are wanting to look at quantum groups that have this property. So here's some other examples. Now, after the Taft algebras came the generalized Taft algebras introduced by Sibbles and Radford, where you kind of let the g and the x have different exponents, but it turns out that they have to be related. So n has to divide t if you want to build a quantum group out of this. And all these quantum groups have a nice property that all their simples are finite dimensional. Not finite dimensional, but actually one dimensional. So let me move on and actually, so here's this proposition that these simple modules of these Hopf algebras, actually simple and also co-modules, are pointed. So in Hopf algebra theory, there are actually two main directions of approach. You can look, there's a direction that looks into semi-simple Hopf algebras. So that means that H comodules or representations of H turns out to be equivalent for finite dimensional Hopf algebras over algebraically closed fields of characteristic 0. They are actually semi-simple categories. So in that case, talking about indecomposables doesn't make that much sense. You just talk about simple modules. But another direction is looking at pointed Hopf algebras. That means that the simple objects in this category of H co-modules, so the simple objects in this category are one-dimensional. Okay, so that's what a pointed Hopf algebra is. Think about it this way: you have a quantum group whose simple modules are one-dimensional, whose simple representations are all one-dimensional points. They're points. They're actual points, right? Just like you know, like you would have a variety, and you talk about points on that variety. So our main result here is that we give a classification of these pointed quantum groups. So this is what this means: quantum groups, which have discrete representation type. And there are some other people who've looked at Hopf algebras of finite representation type, and this, but this has been especially in the finite dimensional world. Farnsteiner has looked, you know, I've mentioned already this classical results, and it's just going to take maybe just a few more minutes. We've already mentioned the classical result for finite groups, and Farnsteiner actually looked at the co-commutative finite dimensional Hopf algebras of finite representation type. So or finite group schemes, and he has results in that direction. And then some people actually looked at pointed finite dimensional Hopf algebras. So exactly what I've said, but in the finite dimensional world. So Liu and Li, they were able to classify quantum groups which are finite dimensional, sort of finite in a sense, and which are pointed and have this finite representation type. And this is actually a combination. So their results show that these type of objects are actually monomial, and their combination also used the results of Sybil and Rosso and Edward Green and a few other people, Chen, Huang, Ye, and Zhang, who classified these monomial Hopf algebras. And what the story is that if you take a finite dimensional quantum group, let's say, and you want it to be pointed and of finite representation type, it's actually one of those Taft algebras or generalized Taft algebras or some algebras that are just slight twist of those. But from the point of view of the category of representations, they are nothing but just modules, or just the path, just the category of modules over that path algebra, cyclic path algebra with the relations that I described. So as a category, they're just that, but then you need the additional tensor structure that makes some difference. Now, in the infinite world, I just want to give a few very interesting examples that are due to first Paragus and then Bichon. So if you look at this example that I put in here, this is yet again a generalization of Taft algebras, and you see that I've actually removed the relation g to the n equals 1. So there's no relation g to the n equals 1. Remove that relation and you still get a Hopf algebra, or you could also do this for the Taft algebra. This is coming from the Sweedler algebra. But what's very interesting about this Hopf algebra, actually Paragus's paper is called Hopf algebras in nature. If you take the co-modules over this Hopf algebra, so again, think of co-modules over this Hopf algebra as just representations of some abstract quantum group. That category is in fact the category of co-modules over the category of co-modules over that Hopf algebra is in fact the category of chain complexes over K. And if you go to the generalized version, the n, you replace the 2 by n, the co-modules over that is the so-called category of n chain complexes, which were considered by Kapranov, and some people were trying to do sort of a quantum homological algebra. You simply declare chain complexes which has the property that differential to the n is equal to 0, not d squared is equal to 0. So these are actually very interesting Hopf algebras that appear in nature. And here's one. So I'm denoting this example here as A infinity infinity. You see this diagram that we see here. This is how you get a chain complex if you take d squared is equal to 0. So H co-modules are really just kind of representations of the infinite line quiver, but just with taking this condition that d squared is equal to 0. And here's one very similar or related example. Consider the category of bicomplexes, right? So you look at this this diagram that you have here. right? So here's how a bicomplex looks like. D squared equals 0 on the vertical and horizontal, and you want to make these squares here commute. This category, or anti-commute, it turns out that the categories are actually equivalent. This category is actually the category of chain or bicomplexes is equivalent. Turns out there's a Hopf algebra such that H co-modules is equivalent to the above category. Okay, so here are some interesting examples, and it turns out that all these categories are exactly a finite representation type in the sense, or discrete representation type in the sense that I mentioned. And you can actually play with this category of bicomplexes, and you can try to fold it. Imagine that you take, it's like this grid, and you try to fold it and make it maybe just identify vertices. So here's this picture over here. So I just identified every 3 vertices, but you can fold it even on diagonal. So it's basically just taking it, like you take z times z and you mod out by some subgroup. That's what a folding is. So I denoted this this by f star star. So here's this notation. And you can also get Hopf algebras in this way. And this example here, I'm actually denoting this example by G, because this is this grid quiver. And our result is actually that these sort of Hopf algebras that appears in nature are exactly classifying the quantum groups of finite representation type, which are pointed, so whose simple modules are points. So that's a result. That's the theorem, and that's the last thing I'm going to say. So the technical theorem is that if you take a pointed Hopf algebra such that the H co-modules have a finite representation type, right? So that means a quantum group of finite representation type, and whose simple modules are pointed, then the category of representations is actually the product of copies of exactly one of these things, either that cyclic quiver, that line quiver, that grid quiver, or the folded, these folded quivers. So this completely describes the category of representations without the tensor structure, but you can actually completely describe also that. So a complete list in terms of generators and relations can be given. And I'm just going to, sorry, I think I'm going over time, but we had a little bit of stops at some point. So I'm going to stop here. If anybody wants to see some more details about exactly how these are defined, I'd be happy to go into that. So let me just stop here, and I'm going to thank you everybody again for paying attention and for being here. Thank you very much.
Let's thank Mio.
Thank you.
So I'm going to stop the recording, so we can ask questions after the recording stops.